Warmly welcome to tonight's conversation. It is part of a new collaboration in science programming between Kulturhuset Stadsteatern and Stockholm University. My name is Johanna Kolgren and I have the pleasure to sit here tonight with Professor Frank Wilczek, the theoretical physicist, Nobel laureate, connected in different professorial capacities to MIT, to Shanghai Jiao Tong University, Arizona State, and our Stockholm University. Thank you, Frank, for taking the time to speak to us tonight. Warm welcome.
Thank you.
So we're surrounded by signs that say Nobel calling. Would you like to take us back to that time? It's 15 years ago now.
Yes.
When there was a call, or was there a call? Is that how it works?
There was a call, and there's a story in my case. So because of the difference in time zones, the formal announcement comes at noontime in Stockholm time, which is 6 o'clock in the morning on the East Coast, which is where I was. I had thought it was possible for several years that we would be getting the Nobel Prize. And so every day, so I knew when it was going to be announced, and the night before I couldn't sleep. This was a regular thing for 4 or 5 years. I had a sleepless night. And we had, at that time, we had a little clock with red digital numerals that told what time it was. And so I wasn't sleeping, and every once in a while I would look at the clock. And it got to be 5 o'clock. And I said, well, look, you're not sleeping. You might as well take a shower just in case, so you would be ready. And so I got up out of bed and went into the shower, and I didn't realize two things. The first thing I didn't realize was that although the formal announcement comes at 12, the phone calls can be earlier. And in fact, at about 10 after 5, my wife came, Betsy, who's here, came with our mobile phone and came to the shower and said, there's someone calling you from Sweden, and they have a very charming accent, and you should probably take this call. And I said, okay. And so I stepped out of the shower. I have been taking I was soaking wet. And I didn't want to keep the other side of the conversation waiting, so I just took the phone, and Betsy dried me off as I was, more or less, as I was talking on the phone, and they said, congratulations, you've won the Nobel Prize. So that was the first thing I didn't know, was what they called early like that. And then the second thing I didn't know that I learned the hard way that morning was that I had envisaged that it would be a matter of they call and say, congratulations, you've won the Nobel Prize, goodbye. But it wasn't that way at all. Several Swedish friends wanted to congratulate, and the secretary of the academy wanted to start explaining the procedures and what you should and shouldn't do and how to respond to the press. And this conversation went on for 20 minutes or so. And meanwhile, I was still soaking wet and shivering. But I enjoyed it. It was like another state of consciousness. And then the first thing I did afterwards, after getting reasonably dry and putting on a robe, was call my parents, which was a very, very special moment, because they had really lived a hard life, struggled through the Depression, and invested a lot in my education and sort of seeing me through. And this for them was very, very special fulfillment. And however, it involved calling my parents at about 5:30 in the morning. So what actually happened when I called was my father was really super grumpy, saying, "Well, do you know what time it is? What do you? I don't. Whatever you're selling, I don't want to buy it." And I said, Dad, he calmed down and explained to him what had happened. And of course, it was a very, very emotional, fulfilling moment for us. So that was the morning. And then somehow a reporter for Time magazine also had advanced information and knocked on our door.
How did they?
I don't know how, or maybe it was at exactly 6 o'clock. Anyway, they
Maybe they staked. So they staked out your house, and
They
they saw that
sta-
the lights were on.
yeah, something like that. I don't know. It's a mystery. But in any case, they knocked at our door and right away started taking pictures. And as soon as the announcement came, the phone, it was just, we'd answer the phone and hang up, and it was still, you hang it up, it was ringing again. So we just took it off the hook, and that was an exciting morning.
You said that you had a feeling. How does that work? How is there a rumor mill? Does the community, the wider physics community, know that it's about time? How does that work?
Well, in my case, I had been told by many people that they had nominated me for the Nobel Prize. I don't know how true these things are, but so I knew that was possible. In all modesty, I thought the work was worthy, and the other factor that came in that made it kind of acute is that there's an order in these things. So our work relied on experimental work and theoretical work by other people. And in previous years, first the experimentalists and then the theorists, who were kind of our the people we built it on most directly, got the prize. So it was it sort of was like a syllogism that we were going to get. Socrates is immortal, and whatever, and that we were going to get.
It's funny.
We were logical consequence.
We're going to talk a little bit later about patterns and symmetries, but I'm starting to see that there's a pattern that emerges. We start to feel that it's your time.
And physics is a small world, so theoretical, and so people have a sense of what's coming and what's up there.
I had to look it up on the internet. It was awarded for the discovery of asymptotic freedom in the theory of strong interaction.
Yes.
So I had to learn a little bit about the basic theory of strong force. And I felt when I read it that I kind of got it, but I couldn't tell you now. So would it be possible to explain this to lay people?
Yeah, absolutely.
It's okay if it's not possible.
Yeah, so there are 4 basic forces of nature, according to our fundamental understanding of physics today. There's gravity and electromagnetism, which have had beautiful, mature theories in the case of gravity since the early 17th century with Newton's synthesis, and then Einstein's theory of gravity in the first part of the 20th century. Then electromagnetism, which had beautiful equations and reached a high level of understanding in the 19th century with Maxwell's equations, which we still use today. And then in the 20th century, when people started examining atoms and the interior of atoms, they found that those 2 forces were not enough. They needed 2 other forces in order to account for what goes on deep inside atoms. One is called the strong force, which is the strongest force in nature, as its name suggests. And what it does is hold protons and neutrons together inside and to make atomic nuclei. I mean, that was the classic formulation of what the strong force is and kind of its most obvious manifestation in nature. because of our work and the way the theory developed, it turns out that protons and neutrons are not the most basic objects. There are things called quarks and gluons that are more fundamental and build up protons and neutrons and atomic nuclei and a lot of other particles too that physicists discovered over the course of the 20th century, especially the later part of the 20th century at particle accelerators. And then there's the weak force, which I won't talk about. It's weak. And so it was a major item on the agenda of physics. I'd say it was, in terms of person hours, PhD hours spent on it, was probably the dominant activity of physics, starting from the 1930s, to figure out what these forces are and what, in particular, what the strong force was. And a lot of experiments were done. There are big, thick books that summarize the measurements, and each measurement represents an enormous effort. But the situation was very confused until some decisive experiments were done that, first of all, indicated that there were these more basic objects inside protons and neutrons called quarks, and then that quarks had simple properties when they're studied at high energies or when they're close together. And making those facts, reconciling those simple facts about the strong interaction with general principles of relativity and quantum mechanics was quite difficult. It was, and it turned out that what we demonstrated is that if you took these very basic clues and demanded that you had a theoretical structure that was fully consistent with relativity and quantum mechanics, and these phenomena that the forces got weaker at short distances, you were led to a basically unique theory of how the force worked. That among other things, said that there should be gluons with very specific properties, and we got precise equations, which to this day are believed to be the equations for the strong force. And so the work was getting to those equations, and then also pointing out consequences that could be tested experimentally, because nuclei are very, very small. It's not easy to investigate their properties, so it was not a trivial thing to draw consequences of these equations that people could actually measure, and that's what we did. And since then, as I said, things get really simple at high energies, according to our theory, and that proved out, but was also very useful because, useful to high energy physicists, because at machines now where the energies are much higher than we had in those days, this predictive behavior is much more evident and guides how you design experiments and how you interpret them. It also opened up the early universe where you had very, very high energies. It made that, instead of being very complicated to study, very simple to study how matter behaves in those conditions.
In case somebody missed some details, we can at least summarize it by saying, and I feel this was very clear, but I do feel that it's obvious that this is it's a major step in a completely fundamental understanding of basically everything.
I think so, yes.
In the world, and that has to. So people for decades or centuries, arguably, but very practically for decades, were trying to solve this,
yes.
And a lot of people had to be wrong. A lot of people had to be incrementally right.
Yes.
But you guys, you and your colleague, cracked it in the end. Do you remember? Was that a specific moment? Is there like a moment? How do you crack something enormous like this?
Well, there was a very central calculation, which was whether the force between quarks gets stronger at short distances or weaker at short distances within different possible consistent theories, where I mean consistent with relativity and quantum mechanics, which is very restrictive, it turns out. And as I mentioned, there's basically a unique theory where the forces become weaker. And people had studied a lot of other theories and never found that behavior. When we realized that the calculation was indicating that the force was becoming weaker, that was certainly a very significant moment.
Did you have to leave your chair and run around the room a little bit?
No. It was kind of an the computations were very complex. And so, I filled up notebooks with these computations that checked them every which way, because really the foundations for these calculations were not very secure at that time. There was a bit of guesswork involved. So I needed consistency checks to calculate the same thing in different ways to make sure I got the same answer. And at first I didn't. The answers are all different. So so the first magic moment was when everything started to be consistent, and then it was more a feeling of relief. I thought, oh my gosh, finally, I got the damn answer. And then, and I was happy to get an answer. And okay, the fact that the forces were getting weaker, that was really interesting, because that was something new. How much leverage it would have, I did not fully realize at first, but it was only a matter of a few weeks, really, from that initial calculation coming together and indicating this behavior, to having a candidate set of equations for the strong interaction, which people had dreamed about for decades, but really very few people expected to see.
Yeah.
For instance, people had studied the forces between protons and neutrons, but instead of finding a simple result, things got more and more complicated the closer you studied. So the fact that you could find really simple behavior inside there was a beautiful surprise. Because
so this was decades earlier, than the prize, of course. So,
yes.
So the question is, what happens when you win the prize? Does it, because you already know what your achievement was,
yes,
and all of your peers know what your achievement was.
Yes.
So what does the Nobel Prize mean in this context?
Well,
Is it like winning the Olympics? It's okay to say that it's just very cool.
It's it's the difference between staring meaningfully into your lover's eyes and sort of getting together. You know that something is happening, but there's another dimension when it actually happens, and that's.
If I get a slightly less fleshy analogy, would be that it's witnessed by the congregation.
It's a personal satisfaction, but it's also a community satisfaction that we recognize that this great problem has really been solved, and sort of now it's official, and and I was really surprised, because by the reaction of my colleagues, some of whom I thought of as rivals, and so, but actually, it was just an outpouring of love. I think that because it was, the work we did was highly leveraged. We built on a lot of other people's work. So it was really recognition of this whole community effort that had succeeded. And
I would love to ask
very-
a little bit because you said the beautiful equations before. You talked about it, and beautiful theories.
Yes.
So I need to ask about that, but I have to ask two more quick questions before we move on from that. One is, this all happened in the 70s, these breakthroughs. So obviously you couldn't just go on Twitter and say, we have solved it.
No.
Did
Well-
you have to call everyone you know and say, I think we've got it?
No, because I wasn't sure we got it, that we had it. No, the experimental data that we were relying on was pretty flimsy at first and indirect. The full simplicity and convincing evidence for the theory only came when the experiments were done at higher energy. So when the bigger accelerators that revealed the simple behavior at high energies were so in undeniable form, I wasn't sure at all that this was the final word. It was really only in the 1990s, I would say, when the large electron-positron collider, LEP, at CERN began to operate, that the evidence became clear and undeniable. And so many of my colleagues were more convinced than I was about the theory. I was willing to entertain that it might be correct and build on it, but I wasn't fully confident, and I thought the phenomena might have some alternative explanation. Maybe
I'm
we were
starting to see
pushing
where
too,
the satisfaction
pushing too
comes
hard
from
on.
being ultimately resolved.
Yes.
Yeah. So you have to have a favorite for the next winner. Would you care to wager who's winning tomorrow?
Who's well,
Speculate.
there are several candidates.
Do you have a favorite?
My favorite? I don't know.
Maybe you're not allowed to say.
That's dangerous territory. But okay, I would. I think it would be fun to recognize the discovery of exoplanets.
Okay.
I think there's also profound progress in the use of quantum mechanics to do computation and treat information in new and powerful ways. But it's not clear to me that that's mature.
Yeah.
It's still very much up in the air, so it's not clear which contributions will be the most important in the long run. And
So probably exoplanets. I don't
no,
know.
I don't.
Still open.
Let me emphasize, I don't have any inside information. No.
I mean,
If
obviously also like I want it to be exoplanets because that one I understand.
Yeah, and it's of course it's not fundamental physics, but as an achievement in application of physics, the optics and the information processing involved is just extraordinary. So it's an extraordinary technical, powerful application of physics, and I think.
And it's like a science fiction dream, which is wonderful also.
Yes, yeah.
So you wrote a few years ago a wonderful book called A Beautiful Question, Finding Nature's Deep Design. And it has a central question, and the central question is this: is the world an embodiment of beautiful ideas? Yes. And phrasing it this way suggests that the ideas would be there first and the embodiment comes later. And this is, of course, an unusual position to take for a scientist today. And you take us in this book on a tour through the history of philosophy and science that explains why you would put it that way. And even so, I think it's a little bit surprising in our culture, in this age, for a physicist to write a wonderful argument that involves art and metaphysics and human anatomy and many other things like this. Could you explain how this book came to be?
Well, when I was, it really grows out of my entire life that when I was a child, I was brought up in the Roman Catholic faith and really took it very, very seriously. So I took it very, very seriously and really thought about that there's another world that's hidden, that describes what this world is really about, that this is really, it's not, that it has meaning, that it has a story to it. And I loved that idea. And I also love the idea that, you know, that ideas have power. But, you know, when I studied science, well, I studied magic first of all, but that was disappointing because it was all trickery. But I studied science, and I, you know, found that there really is a kind of magic. And when I was growing up, there was the time of Sputnik and people, the atomic bomb was a relatively fresh memory. The Cold War was on, so the power of scientists to do really surprising, magical things was very tangible. The space race was going, so I got deeply involved in studying that, and those ideas were not. I wouldn't say were not. They're basically orthogonal to the religious texts, the traditional religious texts on the face of it. So I got very disillusioned and for many years kind of just. There was a void where there used to be these cosmic feelings and things. But as I learned more about science and really studied its history deeply and its human context, I was able to revisit those questions with a new perspective, and that's where the book came from, I think.
I think, I mean...
that's what I was, yeah.
It's a very complex argument, but one of the things that you talk about in this book is that human bodies are, for instance, built to prefer visual input, so
Yes.
that makes us hardwired to care very much about light and also perhaps patterns.
Yes.
You, for instance, also write about why harmony in music is pleasurable,
Yes.
and if I understand it correctly, and we don't exactly know, but probably it has to do with that the brain successfully predicts symmetries in the early stages of perceiving sound, for instance. So again, like there are very obvious physical reasons for us to enjoy harmony.
Oh, I should have said,
symmetry.
I mean, I left out the very important thing,
Yeah.
which is that as I learned more about science, I learned that, at least as far as I'm concerned, there is a beauty to the world, and that's not an accident, because beauty is a human concept and has very much to do with things that you want to revisit, things that you find attractive and that you keep coming back to. Those are the beautiful things. And on the other hand, we are evolved to try to adapt to our environment successfully. And that means we are evolved to enjoy learning how things actually work. So when we learn how things actually work and succeed at it, that's something we find beautiful. And
I find this so compelling.
And it's very nice on the part of nature that it actually behaves that way.
Well, yes, it's incredibly helpful that the things that we find beautiful and interesting,
yes.
When you start to look at scientifically, for instance, what is musical harmony, it turns out that these are mathematical patterns.
Yes.
And that the world and the things that we consider beautiful, including beautiful equations in understanding the world, are in fact, they have predictive capacity. I was astonished when, I think it was when you were writing perhaps about the Maxwell equations or something like that you were talking about how now, the one thing that we learned in the history of science is that beautiful equations with beautiful symmetries tend to be correct. So now these guys, the scientists, sometimes they just make, like, instead of figuring out something and then finding out afterwards, yeah, see, it was right and the equation was beautiful. Now you just make beautiful equations and then first you make them beautiful.
That's very much how our theory of the
strong... realize that's how the world works.
Yes, that's very much how our theory of the strong interaction works. We constructed a beautiful theory. It's very hard to make theories, that I said, that are consistent with relativity and quantum mechanics. They have to have a lot of symmetry because it's almost impossible to put relativity and quantum mechanics together. But the fact that it's almost impossible, but is possible, means that it's very constrained. And the kind of equations that enable you to do it are very limited. And among those, the most symmetric equations turn out to have this behavior that we were looking for in explaining how quarks' forces get weaker at short distances.
So basically that means that the human mind, which is of course the human body, because that's what it is a kind of machine built to understand mathematical relationships, which means that the very thing that makes art powerful and uplifting and enjoyable is also the thing that makes us great scientists, or potentially, as a species, certainly great scientists.
I think they have the same root, that we are, we're built to enjoy understanding and learning and being challenged, and if we don't destroy that feeling, that nature doesn't compel us to destroy it. And Einstein said the most incomprehensible thing about the universe is that it's comprehensible. That's a gift, but that's didn't have to be that way. But it turns out to be that way, and that means the world is beautiful because we can come to comprehend it, and that's the kind of thing that defines beauty, really.
And what is lovely about this, well, many things are lovely about this, but one of the lovely things about this, obviously, is that it opens again for that idea of purpose or intent in the universe. It doesn't, the beauty of this system of which we are part doesn't actually require any kind of God. We have all kinds of very scientific explanations for how it worked out like this, but if we choose to tell ourselves that story, or for those of us who believe in that thing, it's also not in conflict fundamentally with
it has some system. Aspects of what people think of as fundamental religious concepts. I mean, the concept that laws are eternal.
Right.
That there are underlying things that don't change. There's a kind of permanence underneath the ephemeral behavior of many things, including ourselves. The fact that the same laws work everywhere. The scale of things, the internal scale that things. We're very small compared to the universe, but we're very large compared to atoms, and we can have a rich structure because of that. It's just so marvelous. You know?
Yeah, I mean, I realize that this is a dangerous thread to follow in a way, because if we argue, like, if I'm thinking aloud right now, and that's very dangerous. But I'm going to think aloud, and it's obviously that if I personally, for instance, were to accept this model as true, and then I would say, and I also accept all religions that are synchronized with this, or that match this as true. It means that then I have said that some religions are obviously completely wrong on my scientific basis, and that usually doesn't make people who belong to those religions very happy.
Yes, well.
That's a little risky. I need that. You said that you.
One thing that there's not, I have to say, there's no hint in scientific knowledge of a personal God, of a person, something that has the characteristics of a person with a person. The laws seem to be very abstract and mathematical, but they do have some of the characteristics of universality, of timelessness, and of beauty that
So-
that people associate with central concepts of religion.
So I'm going
So
to
you
ask you a
have
hard-
some of it, but not all of it, right?
So you mentioned that you have a Roman Catholic background. Now, and it struck me that I am vaguely aware that, for instance, many Jesuits do have advanced degrees in science.
Yes.
Science.
Oh, yes.
So would you say that it's possible to be, for instance, fully a scientist and fully a Christian, even if that's not where you ended up?
Yes, it is possible. There's although it's a balancing act, and I think it's possible only if you accept the concept of complementarity, which is another profound lesson that I take from science. So complementarity is an idea that was formulated, popularized by Niels Bohr, the great quantum physicist. And it's the idea which is within quantum mechanics is a theorem. It's not optional. It's a feature of quantum mechanics that there are different ways of describing the same object, both of which are valid and even complete in their own terms, but which are mutually incompatible. So in the case of quantum mechanics, you can describe where an electron is likely to be, or you can describe how fast it's likely to move, and you can make full descriptions of either of those, but you can't do both at the same time. That's the Heisenberg uncertainty principle. That's it. So there are different viewpoints. So generalizing that vastly, I think is a really liberating concept of complementarity, that there may be different kinds of questions you can ask about the same thing, about the same phenomena, that require different concepts to answer. Yeah. And those concepts may not be mutually compatible.
I think that's a really good answer.
I think it's the right answer. Yeah. I mean, so a classic case is free will versus determinism. So, although there are some arguments about this, I think to me, it's clear that the basic laws of physics are deterministic. If you had perfect knowledge of the state at one time, you would be able to evolve it forwards, and the equations have unique solutions. So that it's deterministic in that sense. On the other hand, we experience that we make choices.
Yeah.
And if we want to have systems of laws, if we want to punish criminals, if we want to understand other human beings, we need this concept that they actually make choices and have free will. So that's a valid concept to address certain kinds of questions, how people will behave, how they should behave, or how they should be punished. But if you ask about the physical aspect of people, I mean, how they're going to respond to medicine, how they're going to respond to being shot, then free will doesn't come into it so much, right?
No.
Right.
And I mean, if we zoom out even more, and this is the point where I got very blown by the book. It was an observation, and of course now I forgot to note down who made the observation originally, but it's very beautiful. You quote this phrase that objective reality exists, it doesn't change. And now if we add to that, do you remember who that is?
That's Herman Weil.
Yes.
But it actually goes back to St. Augustine. I've been reading St. Augustine recently, and he had this concept that from the God's eye point of view, the world doesn't change. It's all of it. Space, time is all laid out. That space and time shouldn't be thought of as separate entities, but as a complete entity of space-time, and the space-time is just it is.
It is,
It
and
is.
it's therefore sort of finished.
And it's only to us that crawling along our world lines, this is what Herman Weyl said, that it appears to be events unfolding in time.
Yes, because time to us is a dimension and that we're like moving along.
Yes.
But of course, from the perspective of physics, or St. Augustine's God, it turns out, which I didn't know, and it's slightly alarming, but very wise of him as usual. From the point of view of physics, everything has already happened, and then we're back, and then this is the point where my brain melts. I cannot, how do you even think in these concepts?
Well, you
Well,
have
as
to,
a physicist,
you
how
have
do
to
you
use complementarity. You think to address different kinds of questions and different kinds of issues, you have to use different concepts.
Okay, so I understand that we're not meant to understand the sort of fullness of space-time as deterministic on the individual
In everyday
level.
life, yes,
Yeah.
that would be a very dangerous attitude, right?
Yeah.
I mean, who cares? It's all.
But on some
it's
kind of,
all
on a very large
fluid.
scale, everything is done.
Yeah.
Yeah. This is why sometimes ordinary folks find it surprising that scientists are also ordinary folks. Because how can you just continue living with this knowledge of how everything works? Isn't it also alarming and not just...
I mean, first of all, there are plenty of holes in our knowledge. We're not done yet, and conceivably we may have to rethink things we think we know. I mean, at a very basic level, that's happened in the past. But let's suppose it does hold up, this view. Well, I mean, if I want to answer questions about cosmology, the large-scale structure of things, then it's very useful and really very natural to think about space and time as one entity, as space-time. It's very unnatural to separate them, actually. And especially in Einstein's general theory of relativity, it would be almost impossible to separate space and time, and it would be very ugly and unnatural. But okay, but for everyday life, we don't get to see the whole thing. We get to experience a bit at a time unfolding, and you can enjoy that too, right?
You're right, I think in the context of discussing Newton, you're right. Is it not unnatural to separate our understanding of the world into parts that we do not seek to reconcile? It is that query to which this book, your book, for me responds. And I think it's interesting. It just really struck me because I have been trained at university and by living in a secular society to think that the sort of metaphysical and certainly the sort of spiritual or religious approaches to these things they don't have much relevance. However, since I come from the humanities, I am also trained by my education to feel that the arts have profound relevance in answering the big questions of life and existence and helping us understand, helping us grapple with these enormous concepts that we also engage with as humans, especially with humans with this level of scientific knowledge that we have now as a species. So there is something interesting in how arbitrarily these different fields are prioritized or respected, and it feels like it leads me to think two different thoughts. One is I suspect that there's something about how we do science education that is perhaps completely ass backwards, because I may not have ended up in the humanities if somebody had said to me, instead of saying this is hard about physics or at best this is exciting, they would have said this is beautiful. Mm-hmm. And then my other big question is, I wonder if we are at a sort of tipping point that your book is also one example of, where we're saying, okay, the religious explanation models weren't great, but sometimes some ways that we have been engaging with the scientific explanation points, they're perhaps too limited. So yes. What is the worldview in which we can, confront these new challenges that we have set ourselves as a species? Is there some new kind of way of thinking about science and all these things? And these are two different big questions. You can start with either you want, education or like...
Well, I keep coming back to this concept of complementarity, which is that there are different perspectives on the same phenomena, the same object, the same universe that have validity and answer different kinds of questions or respond to different kinds of needs, and you can use both. And how should I say, knowing that the laws of physics are what they are, and the basic constituents of matter are what they are, doesn't get you very far in understanding human beings in everyday life. So you need to be open to both. Now, okay, for most purposes of everyday life, you don't really need to know about quarks and gluons and the equations. On the other hand, it's mind expanding and it's beautiful if you do. Right? So just as you can get by without knowing anything about art or literature, but
it would be terrible.
It's impoverished. Yeah. So science, I think, can be pursued as a vocation that absorbs the important parts of a life, but it can also be. You can enjoy art without being an artist. You can enjoy music without being a professional musician, and so forth. And you can and should enjoy science without necessarily being professional science. Yeah.
I mean, that's a bit of a problem. It's a massive problem, in fact, right now because of the climate crisis that we're in. Most people don't engage with science even a little, to the point where they don't even understand why you have to listen when scientists say this is an emergency.
Well, on the other hand, they enjoy their iPhones and and enjoy the productivity that science has made possible. So maybe they should be reminded that paying attention to reality is a good idea.
If you were allowed to dictate something about how science education would happen in the world, if we gave you a magic wand or some kind of science wand and said, you are now the decider, how would you change science education?
I would teach more of the history of science and how the concepts instead of just saying this is the way it works, say, well, it might have worked this other way, and people thought that for a while, but then we had to give that up because of this phenomena and that phenomena that it couldn't explain. I think it makes it a much richer kind of experience, like a sort of a dialogue between historical and people love narratives and dialogues, and so I think there should be more of that. I also love that. There's another. Okay, so that's kind of conceptual, soft. There's another part of science, though, which is quantitative and logical, but that can also be fun. People really enjoy doing logic puzzles and things like this, and I think that should be encouraged also.
Like the kind of puzzles that you buy in a supermarket.
Yeah. So people do buy them, right? Because they obviously didn't have. No one holds a gun to their head and say you have to solve logic puzzles. They go in and buy the magazines and I think that shouldn't, for children, I think that's really should be encouraged, solving puzzles.
Now,
so active kind of reasoning, yeah.
I actually fully agree with this, that the history of science is a big part of the answer, but it also strikes me that both thinking about the history of science and this development and thinking about the Nobel Prize, which tends to be retroactive for obvious reasons, it does makes us look a little bit backwards. So I thought maybe at the end we would look a little bit forwards before we open up for questions. what is the exciting edge of physics right now? Like, what is the things that you are thrilled to think about in your field right now?
Well, let me not give too parochial an answer because I'm thrilled about things that I've been involved in.
You're alive, by the way. Everybody's here to keep you.
So there are some specific problems that are enormous and ripe, I think. Physics has achieved a remarkably detailed and complete and powerful theory of ordinary matter, the kind of matter we're built out of, that people study in chemistry and engineering and so forth, the matter that's based on protons and neutrons and electrons and photons. But somewhat embarrassingly, astronomers in recent years have discovered that most of the mass in the universe is not any of that. It's something else. And we don't know what it is.
How close are we to solving this problem?
Well, you never know how close you are until you've actually solved it. But I have an idea about what it is called axions that they're predicted to be, they're introduced to solve a fundamental aspect of physical law that appears to be very coincidental in our current formulation of the laws. So not
we don't
very
like
beautiful,
coincidences.
No, we don't like
because we like symmetry.
No,
yeah.
no, that's what we like, symmetry, and we like things to make sense. No, so for instance, a glorious example of this is in Newton's theory of gravity. You always had the force proportional to the mass and the acceleration inversely proportional to the mass, so that the acceleration was independent of the mass. So why should it be independent? Why should everything move the same way in a gravitational field? And in Newton's theory, that was just a coincidence. Those two masses didn't have to have a universal ratio, but that was what led Einstein. That coincidence was what led Einstein to formulate a new theory of gravity. And there were things like that in the weak interaction. There were a variety of different reactions that seemed to have the same intrinsic strength. Why should they have the same intrinsic strength? So you had to formulate, there was a clue that you needed a theory that had extra symmetry. Axions are a way of addressing another aspect of physical law, which appears otherwise to be coincidental, which is that the laws run forwards in time look very accurately the same as the laws run backwards in time. So although everyday life, if you took a movie and ran it backwards, you could tell that it was running backwards. If you look really small at what's happening at the basic level, you find you can't tell the difference if the movie's been running forwards or backwards. The laws are the same, and that's a coincidence. With all the other things we've understood, that's still something that needs explanation.
Wait, but is that weird? Because, isn't it, if time only has a direction for us, would that still be weird if we didn't have a direction in time?
No, well, okay.
Maybe this is a super difficult question, sorry.
No, this is an aspect of fundamental laws that not only appears gratuitous, but makes problems, because now you have to understand how from laws that are reversible in time, you've derived behavior that's not reversible in time. And there's a whole story about that, which involves concepts of entropy and second law of thermodynamics, and also the fact that the universe began in a big bang as
Well, yeah, no, it
opposed
began.
to a
You're
collapse.
right. Yes,
So,
I forgot about that for a moment.
so the actual world, the solution of the equations that we find ourselves embedded in certainly is not symmetric between past and future, but the equations themselves are the laws.
Yeah, no, that doesn't sound
So
right.
that's
So that's solving.
so that's a really embarrassing coincidence, and axions explain it.
So,
And
axioms would be like a mathematical solutions. Can we experimentally? Could we?
they are actual particles with very concrete properties, and they are predicted to be very difficult to observe.
So we haven't observed them yet.
That prediction is successful. So, but also if you run them through the Big Bang using our understanding of the laws and the properties that they need to have if they're going to do their job, you find that they are a very plausible explanation of the astronomer's dark matter. They just right. So now the game is afoot, so to speak. The challenge is, okay, they're difficult to observe, but maybe not impossible. And
Would they be
I and many of my
possible-
colleagues have been trying to design experiments and persuade experimentalists to do these experiments that would detect these.
But do we think that it would be possible? Well, should be possible in like our currently existing detectors.
No, we need new detectors. It's like
Bigger.
bigger, but also more clever in some ways. It's like the challenge that faced early pioneers of radio. How do you design antennas to pick up electromagnetic waves, and how do you just? So this is like that. So this is not electromagnetic waves anymore, but we're trying to detect a new kind of matter, and you need suitable antennas that can pick up this dark matter that interacts with the dark matter and turns it into a signal that we can work with.
I was speaking recently with a scientist from the team that observed the Higgs boson, and
Yes.
and he said that they're pretty excited about perhaps building a detector that's basically, I think it was like the circumference of Switzerland or something like that. But really, what he was very disappointed in, I guess mostly the material scientists and people who build things. He was disappointed that we couldn't build one that's the size of the solar system, because that would be best for to solve the problem. But I mean, are we
Well,
talking?
you-
the
no,
thing
that-
that we need now would it be enough to have one that's basically the size of Switzerland, or like the, or I mean, is this a
It's
solvable
difficult
problem?
to tell. It's difficult to tell. There are ideas that I find very plausible that indicate there should be a whole new world of particles and symmetry called supersymmetry that would be revealed at somewhat higher energies than are currently accessible, because it takes a lot of energy to produce heavy particles, and many of us were hopeful that the LHC would do that, but it hasn't.
No.
And then you have to persuade society and yourself that it's justified to spend another 10 billion euros or something
Especially
to
as
build.
we're moving into
to
sort of
build-
a
to
time of
build-
emergency.
with other
Yeah.
many other competing projects or okay, so that you were asking
But that is
about the future.
clearly very
I get-
exciting.
Yeah, that's exciting, but it's and it's exciting to me personally because I've been involved in that story from the very beginning and continuing. But I would say a sort of broader frontier that's very exciting, that I'm really working on very actively now, is a new concept of information. Information in modern computers and standard computers is based on binary digits or bits that these are things that can take values 0 and 1, and you have a lot of them, and you process it to do all the things that computers do. Now, but in quantum mechanics, the analog of this is a quantum state with two states, a quantum object with two states. That's a very different beast, it turns out. This is and so we call it a qubit instead of a bit, because it's a quantum bit. It's a little joke, a quantum bit. And the properties of quantum bits, when you put a lot of them together, are quite different. It's a richer world with a lot more structure, and there are possibilities for channeling that richer structure to do more powerful calculations.
So because it can do it can do 1 or 0, or is it both?
In between, yeah, it can do a lot of in between. So it's a different beast. And it's harder to deal with in many ways. It's more delicate, but potentially more powerful. So coming to terms with how you use that poses many, many interesting challenges and questions. And I think that's a growth area for the future. So quantum computing probably is what the buzzword that most people have heard, but it's a much broader subject of coming to terms with the quantum world, because now our technologies are becoming so powerful that we can really do that.
So basically the technology is kind of catching up with the theory.
Yes.
And now both need to be pushing ahead together.
Yes, yes.
Which means that if somebody here is a student, this is a terribly exciting field to get into, because the next couple of decades are going to be insane.
Yes. I think that's right.
I think, I realize we have to open for questions, but perhaps we can summarize what we've said so far by thinking, or it made me think, I was thinking about Large Hadron Collider, which if you ever have the opportunity to go to CERN, there are tours, you can go and see, and the Atlas detector is like a 5-story building, and it's one of the most beautiful things I have ever seen. And when we think it's like a cathedral, but so is science. This idea that scientific knowledge is a kind of cathedral that is built by craftsmen who over time tend to become anonymous, over the centuries. We don't remember everybody's names anymore. But creating this beautiful monument of understanding. And it somehow connects these things. And now these are the new spires that we're working on.
Right. And the new spires are kind of phantasmagorical. Quantum mechanics is a beautiful thing. It's a little hard to convey without a long story. But it's really mind-expanding, and I highly recommend it.
Yeah, mind expanding, yes. So also it's as opposed to many other things that are mind expanding, it's completely legal, which is also wonderful, much healthier. I think we are ready for some audience questions. Don't be shy. There are no stupid. There's somebody who isn't shy at all, who is going to have a microphone that comes right there. And let's try and keep the questions a little bit concise so that we can have more of them. Yes.
Okay, hello, my name is Gustav, and I'm a physicist, so I love understanding things. But I have to admit that the statement that you had that a life without understanding or appreciating art was impoverished rubbed me the wrong way. And I have to ask you if you see it as a necessity to be able to appreciate beauty, to have understanding of art, how the world works.
No, no. There are. I know physicists, very good physicists, who, for instance, hate music. If they run the other way if there's music, and many scientists aren't interested in art. In my experience, the best scientists tend to do have an appreciation of many different things. The most creative, I shouldn't say necessarily. But it's not necessary. No, it's not. You can. I guess maybe what I should say. Okay, an appropriate thing to say is that certainly in modern theoretical physics, it's very separated from everyday life. And when you're trying to make progress, if you're trying to find new equations or design new objects or materials, we don't have much to go on except a kind of aesthetic feeling. Okay, we're not making analogies from everyday life so much. We're trying to think, how could things be more beautiful? How could things? And when you have a good idea, you sort of recognize that it's on the right track because things make sense and click together and are more beautiful. So it doesn't have to be art in the sense of painting or sculpture or Campbell soup cans or whatever. But I think this kind of aesthetic feeling within science is really essential to doing the very best work.
Yeah, you also say in the book that or you remind us in the book that of the sort of kind of obvious. It should be obvious that of course it's also many of these of the arts are languages or skill sets in a way.
Yes.
That's the brain can like simple harmonies before it likes complex harmonies.
Yes.
So if you're confronted with art that you're not enjoying at all, it might be because there are some previous stages that you haven't had access to.
Oh, very much so.
It doesn't necessarily mean that you don't have that your brain wouldn't enjoy that sort of thing at all. But then would you go so far as to argue that exposing yourself to the arts in different ways is a good kind of training for at least in having some kind of plasticity in your approach to scientific problems?
Well, I don't think it hurts. Whether it's the most efficient way, I don't know, but it's an enriching aspect of human life, and I think it can help.
Yeah.
And I think, but it's more. I'm not sure it's cause and effect, but I think the desire to kind of expand your mind and look at things in different ways that leads you to science and creative work in science also leads you to be interested in other things.
Well, I mean, as a humanist, I would say that it's also about being interested in the impossible.
Yes.
Being interested in the things that are not yet there.
Yes.
That's what the arts are about for me, and I suppose that's also what the science would be about. Thank you so much for this question. Do we have another one? Yes.
Hello. Another question on aesthetics and elementary particles.
Uh-huh.
But first off, how many pens do you have in your breast pocket?
How many pens do you have in your breast pocket?
Fantastic.
I don't know exactly. It's probably about 10.
I'm sure there's a good reason for that. Yeah.
There's a very good reason.
You don't want to be left without. Yes. Okay.
Anyway, go
What's
ahead.
the other question?
Quartz. Being a layman myself, what I know about quarks is that they have a number of different properties and they are small.
Yes.
But it's very hard for me to get my head around the concept. And you've been mentioning here today that we as human are visual beings. We like to see things in patterns. So I was wondering, when you study quarks with your profound knowledge of the concept, do you have a mental image of quarks? Do you see them in your studies?
Well, I use many different kinds of images in different contexts. But the properties of quarks are so different from the kinds of things we deal with in everyday life that the mental images are dangerous. They have limited validity. On the one hand, but I should make a general comment, which is that human beings are highly visual information processors. That's what we're really good at, and it's an amazing thing. We can take images that arise through these tiny holes and are projected on the retina in two-dimensional patterns and construct a world of objects in 3 dimensions that we can move around in with colors, and we know something about the chemistry and objects. And we do that really fast and effortlessly. Computers are better than humans at many, many things, like chess and Go and arithmetic. But humans are much, much better at visual processing, and a lot of our brain is devoted to that. So if we can bring in those modules, that visual processing, it's very, very powerful. So I always try to make visual models. In the case of quarks, it's not, I don't visualize them, well, in any one way, but different ways in different contexts. But really, in that case, more what I visualize is the equations and how the equations might be rearranged, or not the quarks as objects, but the underlying fields and the fluctuations in those fields. So the construction of visual models is a creative process that has to be conditioned by the strange properties of the things you're trying to deal with. And so,
hang on, there was a movie, wasn't there, called A Beautiful Mind, I think there was, and he was playing pool and you could see the equations in the air. Do you sometimes see equations in the air? That's a physicist thing?
I can't say that I literally hallucinate equations. but
visualize, not hallucinate.
I do visualize, but I still find it helpful to actually write them down sometimes on a, but not necessarily. But have what I frequently find. This is really everyday kind of experience. Is okay. I work with equations during the day and write them down. But then then I put them away, and my mind keeps working, and it's working, I think, using the same kind of hardware that's used for visual processing. So the things get rearranged, reprocessed, and so I don't literally see anything, but I have a feeling
because the brain is doing the thing.
I have a feeling that that's what's going on. It's just like Beethoven was deaf when he was composing in his later career, so he didn't literally hear the music.
Yeah.
But he did.
In
a real sense, he was able to deal with the information as if it were sound, because he had a different representation that was so powerful that it didn't need to be air vibrating.
I remember also now there's a scene in The West Wing where Toby Ziegler, who's a speechwriter, is writing. He's playing pool as well, in fact. And then somebody says, "Aren't you supposed to be writing a speech?" And he says, "Paper is for wussies." And then he says the sentence that he's thinking. It's exactly this. Maybe this is a universal phenomenon. Yes, we had a question in the back. Just yes.
Well, good evening, and thank you so much for this interesting talk, both of you. I've been thinking about what you've been saying about beauty and about it being symmetrical, and how it being symmetrical means it makes sense, and therefore it's beautiful. So sort of the definition of beauty is sort of contingent or dependent on this symmetry. And me coming from the arts, I'm wondering if we look at the theories of beauty that exist within, for example, painting, dating back to the Renaissance time, we have something called the golden ratio, where we have the 70-30%, which is perceived as beautiful. And it means that, for example, for those that don't know the golden ratio, that if you were to paint a landscape, you would have 30% sky and 70% earth. And that would be, the perfect.
That works.
Yes, that would be beautiful in that sense. But it's not symmetrical.
No.
if you think about it. So I'm wondering if the theory of what's beautiful within science and the theory of what's beautiful within art are in some way conflicting.
No, I wouldn't say they're conflicting, on the contrary, but I think they have commonalities, but I don't think the only form of beauty is symmetry, nor is every aspect of science and physical law beautiful. I mean, so symmetry is certainly part of science, and it's especially central in our deepest understanding of the fundamental laws. And it's certainly also an important aspect of art. The whole concept of perspective, for instance, is based on symmetric and geometric constructions, and people find when they, for instance, a very convincing example, I think, is in decorative art. If you look at catalogs of what people have used across many civilizations to decorate walls or vases, or so, they use symmetrical patterns enormously much, and especially actually when they're trying to depict the sacred inside mosques or inside cathedrals, you find symmetric arrangements of things. But it doesn't exhaust art. There's many other things that people find beautiful for other reasons than understanding how the world works at a physical level. I mean, of course, people also relate to other people, and so a lot of art has to do with the human form, which is not particularly symmetric, or landscapes, which are not particularly symmetric. So symmetry doesn't exhaust art by any means, nor does it exhaust science, but it is a common theme that is really deep in both, and is common. For profound reasons that we've discussed.
And I mean, I think also the golden ratio could also be expressed as a sort of recurring. I mean, sometimes you see it drawn as a sort of spiral, as a shell shape. Or
yes.
That it's also like recurring proportions.
Yeah, the golden ratio occurs in many, many different contexts.
Yeah, and that would make it related in the same way as harmonies can be expressed. I learned yesterday from Frank's book that if you look at it mathematically, the musical harmony, of course, is also about like recurring proportions and between these frequencies, which is obvious when you think about it. But I've never thought about
that
it.
was
I was
kind of
mind blown.
That was, in a way, I would say, the very first scientific discovery. This was by Pythagoras, that the notes that sound well together are the notes associated with strings, plucking strings whose lengths have simple ratios. So these kinds of regular correspondences between the physical world and our perception of beauty go way back. They're still not very well understood. That one in particular is still kind of mysterious, why we find it pleasing to have notes that whose frequencies are in simple whole number ratios. That's I don't think well understood at a physiological level, but it's a fact about the world, and as I said, it was probably among the very first non-trivial laws that people discovered. So it was not a law that related to motion or time, but really to the relationship between perception of beauty and physical lengths.
Yeah, and I mean, and it's also fun because we think of Pythagoras as a mathematician first and foremost, right? But here we are again with the scientists doing you know, if he was doing, but let's assume that it was him doing these kinds of practical things and theoretical things,
Oh, and
and
he
also
was-
placing at the very edge where it becomes, where it's still incomprehensible and sort of gets to that metaphysical level.
Yeah, and he was also a cult leader. He was very much a
Like an actual cult, religious
an
cult
actual
leader.
cult. Yeah, but it was a unique cult. It was a cult of numbers. They
Maybe that's the answer. I said, shouldn't we need some kind of new
But they had-
worldview? Maybe that's what
There
we
was the
need.
Pythagorean Brotherhood, and they also had lots of women, actually, for that time, very unusual, that believed that all things are numbers. That was kind of the leading principle of this cult, and they tried to explain the structure of the universe based on numerical proportions. So in some ways it has the same spirit as modern physics, although the mathematics was relatively primitive, but
And I think
It's on
like,
the
it's
right-
like modern physics, but with a lot more wine, and a little bit less like scientific basis. All right, let's do one more. Perhaps two, if we're like, there's somewhere there's microphone.
Hi,
Yes.
I'm here.
Yes.
Firstly, thank you so much for an incredibly interesting talk. It has really brightened up an otherwise dull Monday. And I'd like to ask, I feel that many fields in this day and age are undergoing a change and growing more diverse, but the scientific community is not really giving off that impression. So I'm asking you, who is on the inside, do you have another view on that? Do you feel that it is more diverse than we give it credit for?
When it comes to things like gender and ethnicity, you think? for instance,
Yeah.
or- yeah.
Exactly.
Yeah.
no, it's not more diverse than you give it credit for.
That's great news.
We're working on it. I mean, I think there's an active will to try to rectify that situation. I think I would be happier, and I think most of my colleagues would be happier to have a more representative balance of, and you know, I would just like to tell women not to be afraid, and that there's there are wonderful things that you can enjoy and contribute to.
Yeah.
And
Do you
So,
think that it's that the work environments are changing?
the work environments are definitely changing,
Yeah.
yeah. And
Yeah.
so
So no, but
please
hopeful.
join in, join the party. We want you. Yeah, and I would hope for some of the ideas we talked about, that that science is not separate or shouldn't be separate from art and music or other human endeavors, and that it should also be regarded as, or should be regarded as, or can be profitably thought of as, among other things, a historical process, a kind of dialogue and narrative. I think these things could make it more universally appealing.
Yeah.
Yeah.
I think we have time for one more. Yes.
Hello, and thank you for the discussion, Mr. Wolczek. I would like to ask about the problem of consciousness, human or not, and widely in scientific fields and otherwise, it's often treated as a problem of second priority, even though science, in my opinion, is essentially a part of consciousness as we're thinking about it, right? Why do you think it's justified that we do not have it as the largest priority? Why do you think that's justified, and why do you think we do that?
Okay, so let me first. I'll answer this in the style of complementarity. Okay,
Okay.
So the first thing I would claim is that there's no evidence at all that there's such a thing as mind distinct from matter. So when physicists or scientists in general do experiments in modern technology, very delicate experiments, measurements of great sensitivity, they have to make all kinds of corrections. They have to make sure that the temperature is under control and the pressure is under control, that you shield from electromagnetic signals, that things don't shake, all kinds of things. But one thing that they've never had to take into account is what people were thinking. So there's, I think, overwhelming evidence, or overwhelming circumstantial evidence that matter sort of can be understood in its own terms without referring to a conscious thought waves or conscious interventions of things that are affecting matter. There's also, I think, based on modern experience with computing machines, that more and more do things that people once thought would require mind as a separate entity. With computers, we definitely know how they're made, and they're made of designed on physical principles and operate by known physical laws, and yet they'll beat you at chess, they'll beat you at Go, and so they do things that were once thought to be the province of mind and uniquely of mind and intelligence. So I think based on things like that, there's a very strong case that mind emerges from matter. Mm-hmm. So that's one side of the complementarity. On the other hand, consciousness is the way we experience the world and the way we construct our models of the world is based on mind. It's based on conscious perception, and that, although it may emerge from matter, looks back on matter and makes sense of it. So these are complementary aspects. You can't. I think there's every reason to think that mind emerges from matter and doesn't need a separate explanation. But on the other hand, it's mind that experiences matter, and without mind, who cares? No one would care, right? And so the questions wouldn't arise. I'm not sure where I'm going with this, but they're complementary. I guess what I really want to emphasize is that the statement that mind emerges from matter in no way diminishes what mind is. It enhances it, because it means you can relate it to other phenomena and experiences, and you can enhance your understanding of it. So it doesn't, the idea that mind should be free of matter could have been true, doesn't seem to be true, but in retrospect, knowing that it may not be true is a real challenge. So now Mr. Physicist, Mr. Neurobiologist, or Mrs. Neuro, how do you? Okay, now you have the challenge. Okay, so matter doesn't seem. I mean, it's not obvious how consciousness as experience emerges from our equations that describe matter. I don't think there are any showstoppers, and people are gradually understanding more and more about neurobiology, and so far they haven't had to introduce new physical entities or new physical laws. It's just molecules all the way down. But we learn that matter has potentials and abilities that weren't obvious at all. And so that very much, I mean, is that fact that matter can think and talk and perform on stage, that's a very remarkable thing. That's a challenge to explain. How do you get from the laws to these, abstract, strange laws of quantum mechanics to that?
Well, it feels like
That-
that
that to me
summarizes
is- you-
everything we've talked about tonight, right?
Yeah. That's what I should.
Yeah.
That's what I should have said in answer to your question about the future of physics. So there are concrete problems. I should have said this. Yeah. So there are concrete problems like the dark matter and axions. There is this frontier of quantum information, and to me, the third great problem for the future is understanding how mind emerges from matter.
That's wonderful.
Yeah.
So here we have, laws of nature create these meat states in our minds that can
Yes.
that can reflect on the laws of the cosmos. It's fantastic.
Yes.
We're going to have to end
Yes.
here. I don't see any nobler point that we could end on. In fact, dear friends, Frank Wilczek.
All right. Thank you.